In the meantime, people will come in. You can still introduce yourself in the chat if you want to. So hello, everyone, and welcome to this webinar organized by Iscarsah and the Association for Preservation Technologies Preservation Engineering Technical Committee. In short, that's APT PETC. Today's topic of the webinar is structural interventions in heritage, and we will look at those interventions through the lens of the Iscarsah Principles. My name is Tim Michiels. I am a structural engineer at Old Structures Engineering in New York and a professor at Columbia University and a proud member of both Iscarsah and APT PETC. Moderating this webinar with me is the co-chair of PETC, Rachel Will from WJE in Chicago. One of the main reasons we are organizing this joint webinar is that there is a great overlap within the work of Iscarsah and APT PETC. Both organizations have members with a wealth of experience in intervention in historic buildings, and we believe that knowledge sharing, or at a minimum awareness of each other's work, will strengthen the field of heritage preservation globally. To that end, I will briefly present Iscarsah, Rachel will present APT PETC, and then we will turn it over to our speakers. ICOMOS Iscarsah is the International Scientific Committee on the Analysis and Restoration of Structures of Architectural Heritage. It's a scientific committee of the International Council of Monuments and Sites, ICOMOS. Sometimes nicknamed within ICOMOS as the Structures Committee, we are truly an international group of engineers, architects, scientists, and educators dedicated to the restoration and care of built heritage. We do focus mostly on the structural and technical aspects of conservation of architectural heritage. We have a diverse board. With at the helm our president, Paolo Lorenzo, and our secretary general is Tom Morrison, a past APT PETC chair. There's a lot of overlap here, as you can see. The goals of Iscarsah are, amongst others, to disseminate knowledge, promote international cooperation, and organize international training programs. Another goal is to collaborate with other scientific committees. And at Iscarsah in 2003, we published the Principles for the Analysis, Conservation, and Structural Restoration of Architectural Heritage. This is about a 3-page long seminal document, which is available for free in 10 languages on our website. We highly recommend you check it out. If someone can post the link to it in the chat, that would be greatly appreciated. And much more in-depth guidelines for the analysis and restorations of heritage structures is also available on our website. We publish newsletters and a bulletin. We organize several free webinars each year, all of which can be found on our website and YouTube channel. Also a small plug for our next webinar, which will deal with structures of heritage affected by war. That webinar is anticipated in late spring. We organize workshops. The last ones were in Iran, Korea, Japan, and Romania. And our next meeting will be in September at the Structural Analysis of Historical Constructions Conference in Lausanne. You can reach us at iscarsah@gmail.com, follow us on Facebook, or find our website. And with that, I would like to turn it over to Rachel, who will introduce the Preservation Engineering Technical Committee of APT.
Thanks so much, Tim. And as we're listening to that, you'll see that there's a lot of similarities between these two organizations. So I'm really excited about this collaboration today. I am one of the 3 co-chairs for the Preservation Engineering Technical Committee of APT, and it was created in 2003 to provide a focus for discussing issues related to engineering and historic preservation. Some of the committee's current initiatives include a student design build competition, which is a hands-on challenge for students with an interest in historic buildings and structures. It was an opportunity to look at some of our engineering students and get them interested in heritage materials and heritage structures. And it's been ongoing. This is actually the 10th year. So I put the information in the chat, but the Masonry Arch and is our competition this year, and phase 1 submissions are due March 10th. Phase 1 is very simple. It's really the students identifying an arch that they would like to study and indicating commitment to the competition. So if you are a teacher, or if you're a professor, if you have any interaction with students, this is a great opportunity to get them a little bit more exposure to the field of preservation engineering. One of our other initiatives is the Disaster Response Initiative, or DRI. It's a task group which is spearheaded by the the Preservation Engineering Technical Committee and has been active in researching and developing strategies for education, partnership, and outreach on bringing awareness to heritage structures that are vulnerable to natural and man-made disasters. So it sounds like the upcoming webinar that you're having relative to war would be a really great one for our dry folks to collaborate on. The goals of that committee or that task group are really to aid local and federal governments and like-minded organizations involved in disaster response. This is also one of the things the task group is also exploring is how to best prepare at-risk communities in light of these hazards. And as Tim mentioned, similarly, PETC is responsible for hosting workshops, conference sessions at the National Conference for APT, webinars, networking events. So really look for opportunities for our two organizations to collaborate in future. But the last initiative that we have is really, really important that we talk about it today because some of our presenters are actually recipients of this award. It's the David Fischetti Award, which is an award for an outstanding article that advances the field of conservation engineering. And so what it is articles must address technical aspects of engineering as they relate to historic preservation. And this is really thinking about, David Fischetti was a preservation engineer, but really taking a practical approach to preservation engineering. So hopefully you will see that in the presentation that Arun and Casey give us in a few minutes here, but they were the recipients in 2024. We will provide information to this group. Hopefully we get quite a few submissions, but submissions will be due May 30th of this year. And it can be an article over the last couple of years, so it doesn't have to be something that was published in 2024. So if you're interested, just please email us at petc@apti.org. I think with that, I am going to introduce our webinar and our speakers today. So today's webinar is about the diagnosis and repair of architectural heritage structures, which often presents unique challenges, particularly when traditional construction methods do not align with modern codes and standards, which we see all the time. So in such cases, engineers can rely on a set of internationally recognized principles to guide informed analysis. This webinar will showcase studies from India and the United States and demonstrate how these principles can be applied in various local contexts. As mentioned before, it will highlight the work of Dr. Arun Menon and Dr. Krishnachan, who won the 2024 David Fischetti Award, and will be followed by a presentation by Terry Perret. Just to give you a quick overview of our first two speakers. Arun is a professor of structural engineering at IIT Madras and holds a first degree in architecture and PhD in earthquake engineering from the University of Pavia. And as mentioned, his full bio was submitted as part of this webinar. So we're going to try to get into this very quickly, but he was one of the co-authors and of the David Fischetti Award article. And Casey has a primary specialization in structural assessment, retrofit, and conservation of existing buildings, and has been serving the AEC industry for close to a decade. And he is one of the co-authors for the Fischetti article. So with that, I'm going to turn it over to them to start their presentation. And then we will have a following presentation by Terry. And then there's lots of opportunity for questions and commentary following that. All right. We can see your screen. It's in the slide sorter version. Dr. Menon.
Can you hear me?
Now we can.
Let me just turn on my camera.
We lost your screen.
Yeah, because I wasn't able to see the video button.
Okay.
Thank you. Thank you very much, Rachel. A very good morning, good afternoon, or good evening to all the participants who have joined this webinar. Thanks to both Iscarsah and PETC, APT from my co-author, Krishna Chandran, and myself. The title of our presentation is Re-engineering the Traditional Madras Terrace Slab System. And my presentation is organized in this manner. After an introduction of the traditional Madras terrace construction, its behavior under gravity and lateral loads, the potential weakness and eventual need for improvement of the lateral load behavior will be discussed. My colleague Casey will then present the experimental, numerical, and analytical studies under both as-built and upgraded configurations of the slab. The Madras terrace slab for floors and roofs is basically a thermally efficient traditional construction system prevalent in the erstwhile Madras Presidency in South India from the pre-British era, basically conceived with gravity as the primary structural loading in a region of low seismic activity. The flow diaphragm is basically constituted of closely spaced wooden rafters spanning across walls. In turn, these rafters support burnt clay brick placed on edge and bonded with lime mortar. They are arranged in a diagonal fashion, starting from the corner and finally topped by a layer of broken brick lime concrete and any finish that is required, architectural finish that is required eventually. A typical layout of the supporting timber joists spanning between walls and the closely spaced rafters placed orthogonally can be seen in this figure on the left. The sockets in the wall where the rafters are embedded and the diagonal brick on edge pattern of the masonry overlay are also shown. A construction system that finds its roots in the pre-colonial era in the region went through a series of formal engineering iterations and finally found its way into the Bureau of Indian Standards, a code of practice in the 1980s. This is a robust construction system where repairs or replacements of the timber rafters can actually be carried out from the soffit without disturbing either the brickwork or the lime concrete. Unfortunately, standard rehabilitation practice has been to completely dismantle the slab and replace it with a reinforced concrete slab, especially in the recent years, citing potentially poor performance under seismic action, with the revisions of the earthquake safety standards and requirements for existing masonry buildings. In this context, with an aim to holistically achieve the preservation of this traditional construction system while addressing structural safety concerns that our study itself was designed. The SDGs 2030, particularly SDG 9, addresses the need to upgrade and retrofit existing infrastructure, making them resilient to natural disasters, while also ensuring that emissions from the construction industry are minimized as much as possible. Culture serves to achieve such SDGs through an exercise of preserving traditional knowledge systems, which is an intangible cultural heritage, and finding relevance in a safer and an environmentally conscious solution. as expounded by the Iscarsah Principles, a multidisciplinary approach is required, with structural engineering becoming the enabler, providing the scientific support necessary to obtain the expected result, namely the safeguard of the building as a whole with the lowest possible consequences on heritage values. Again, guided by Iscarsah Principles, an attempt must be made to improve and complement structural behavior of historical components of systems as against wholesale replacement with modern systems, and at the same time recognizing the limitations of modern codes and conventional approaches. All such interventions in historical buildings must essentially address compatibility with the original construction, materials and techniques, durability, non-invasiveness, removability, controllability, and sustainability. This brings us to the role of such flow diaphragms in the seismic performance and assessment of existing masonry constructions. The assessment and retrofit must attempt to identify potential weak links in the seismic load and resistance path. To ensure satisfactory box action in masonry buildings, possible local out-of-plane mechanisms must be identified and prevented through level 1 interventions that address wall-to-wall connections, wall-to-diaphragm connections, and so on. The critical role of the floor and the roof slabs in the seismic resisting path cannot be overstated, and its in-plane stiffness classification and response is crucial in preventing local mechanisms before any in-plane strengthening of walls is adopted as level 2 global lateral capacity improvement. This is a typical approach that's adopted for masonry constructions. Now, particularly with respect to the role of the diaphragm, while characterizing a diaphragm's in-plane behavior, it is clear that the degree of in-plane stiffness of the diaphragm will determine how lateral forces will be distributed to the load-bearing walls. If it's a rigid diaphragm, you have the distribution based on the relative stiffnesses, whereas if it is a flexible diaphragm, the distribution depends on the tributary areas. The total in-plane diaphragm displacements are composed of rigid translations and rotations and flexural and shear deformations. While at the two ends of the spectrum of in-plane diaphragm period of vibration versus diaphragm displacement, a rigid, well-connected diaphragm and a flexible, well-connected diaphragm would have the least vulnerability in terms of increasing diaphragm deformations being transferred to the supporting walls. But the case is quite different with respect to stiff and semi-flexible walls, with the maximum demand of diaphragm displacements coming onto the supporting walls. So it's in this context that the study has been undertaken. Over to you, Casey, for the rest of the presentation. Thank you.
Good morning, good evening. I hope everyone is able to see my screen. In the next part of this presentation, I'll be dealing with the characterization of this traditional construction typology called Madras slabs and how an improved structural performance for the system was achieved through minimalistic interventions. To understand the response of Madras slabs and identify the potential weaknesses, the first step is to characterize the structural response of the same in the as-built or the original configuration. It is well accepted that the lateral response of Madras Terrace slab has limitations. However, this needs to be quantified adequately, for which the lateral response of Madras Terrace slab was studied using a full-scale experimental test in the original configuration. The test specimen was prepared at the Structural Engineering Laboratory of IIT Madras. The following images shows the steps involved in the same, starting from placement of the timber joists, followed by the laying of the brick masonry overlay, and finally, the placement of the lime concrete overlay. Further, a loading tree setup was created so as to distribute the actuator loads to each timber joist, thereby closely simulating the deform profile of the slab under inertial loads. Displacement control loading was applied through the actuator, and LVDTs were placed at relevant points, both in the overlay as well as the timber joist, to monitor the displacements. After the loads were applied, the deform profile of the diaphragm showed significant sliding in the timber joist due to a lack of integral action between the joist and the overlay. Sliding of the joist commenced at a load of approximately 17 kN, and therefore it was inferred that a lack of integral action between the timber joist and the overlay is the principal weakness associated with the system under lateral loads. As the next step, a retrofit intervention was introduced to improve the system in terms of bringing in integral action between the joist and the overlay. The intervention was minimalist in nature, without affecting the appearance and the positive attributes of the original system, but upgrading it for improved seismic performance. The upgrade involved post-installed anchor rods drilled from the underside of the joist, acting as a shear connector that integrates the joist and the overlay. The same loading protocol, which was used for the test in the original configuration, was used here as well. Results showed that there was no sliding at all in the timber joist, as shown in the image here, and a uniform deformation response of the slab was achieved in the image below. Further, as shown in the image, it was observed that the failure was no more defined by the sliding of the joist, and it was defined by the flexural cracking of the overlay. Comparison of the force deformation responses in the as-built and the upgraded configurations showed that there has been a significant strength capacity enhancement, close to 4 times for the upgraded configuration. This was a major improvement in the capacity of the system, as it changes the hierarchy of weak links in the system by extracting the full capacity of the slab, making it less vulnerable and delaying its failure compared to other members of the lateral load resisting system. While upgrading such traditional systems, it's also important to check if the upgrade brings new effects to the overall system response, and we need to address the same. One such effect that was observed was the rotation of the overlay as a macro block post-cracking. This results in displacements perpendicular to the loading direction and also could cause out-of-plane demands on the cross walls supporting the slab. This aspect needs to be addressed in the out-of-plane assessment of these cross walls, considering combined in-plane and out-of-plane effects for the same, which was undertaken as part of another study. This is very important since this upgrade of one weak link, that is the diaphragm, should not result in effects that create new weak links, even though these may be less critical in terms of their weaknesses. Our experimental results were further verified and validated with numerical studies that successfully replicated the failure profiles and capacity curves from experimental tests. Based on the same, a simplified analytical model was defined for the upgraded Madras Terrace slab, which is useful for practicing engineers as well. The model is defined by a stage 1, which utilizes the integral action of the overlay and the joists for defining the elastic stiffness and the cracking load of the system. Stage 2 is defined by the post-cracking response of the overlay, and stage 3 is defined by the attainment of peak drift of the system. Now, the conceptual understanding of the response of the Madras Terrace slab was not limited only to the upgrade of existing slabs. As the next step, the understanding was extended to introduce a re-engineered form of the traditional slabs that fits into the modern design fundamentals. This included setting up of design guidelines for the gravity design of the slab, considering partial to full composite action between the overlay and the joists through shear connectors. It is useful to point out here that the traditional system was relying only on the interface friction for shear transfer. The design process involves arriving at the optimum size and spacing of shear connectors to ensure integral action between the overlay and the joists, both from gravity as well as lateral load considerations. The design also considers effective stiffness of the composite action for long-term deflection considerations, which now resolves the long-term deflection issues and the sagging of the timber joists due to non-composite action. In addition, the presence of tensile elements in the form of timber joists can be utilized as collector elements for the drag force transfer and also as cords in the slab. Summarizing, many of the time-tested structural systems with significant positive attributes get replaced with newer structural systems over time. When the bounds of our knowledge and the technical advancements in the subject domain get broadened, it is expected that the inefficiencies and weaknesses associated with these traditional systems get identified. However, in the process of trying to resolve these weaknesses, we tend to overlook their positive attributes and replace the structural system with newer ones. However, there could be an option to improve the structural system, re-engineer it, or in other words, improve the structural system. In this study, we attempted to upgrade the Madras Terrace slab for the identified deficiencies using modern technologies with minimalist interventions, bringing in composite action to the system and retaining the original materials and appearance. Experimental testing was carried out in the existing configuration and the upgraded configuration, and results indicate significant improvement in the ultimate load capacity and the post-yield response due to the upgrade. Finally, the understanding was also extended to introduce a re-engineered form of the slab that fits into the modern design fundamentals. Thank you.
Thank you so much, Dr. Casey and Dr. Arun. I want to remind everyone that if you have questions, please save them. We will ask them at the end, but you don't need to save them. You can post them in the chat right now, and we can either address them in the chat or we will feed them to the speakers later on. With that, we will move on to our second speaker. Terrace Terrace is a senior principal at Jenny Elsner, where for 39 years he has performed hundreds of engineering investigations in the US and abroad, focusing on the evaluation of existing structures in a seismic context. He specializes in large, complex, and unique projects where preservation is a priority. His full biography was sent out. It would take me a very long time to describe all his very impressive accomplishments. So Terry, please take it away.
You bet. Let me start sharing. Can you all see that? Oh, not yet.
Not
yet.
Now you should be able to see it. Okay. Thank you all for joining this and listening to this presentation. I'm going to be speaking to you today about the implementation of the Iscarsah Principles, really the ethos of the Iscarsah Principles, more than the principles themselves, but in a seismic context. And I hope to talk about three projects that you see on the screen: a seismic vulnerability project, an ordnance required strengthening project, and a post-earthquake repair project. But to be perfectly honest, unless we've entered a time warp, a wormhole with some time warp, I'll never get to the third project, and I apologize for that. But I hope the first two will entertain you adequately. I'd like to start with a few random thoughts about the Iscarsah Principles themselves. For many of you are going to be familiar with the Iscarsah Principles. Some of you perhaps not so much, but the principles are fundamentally high-level guidance. They are philosophical, not procedural. In my view, that's probably a plus, right? Because one of the problems we have in our discipline is the use of methodologies on highly nuanced heritage structures, right? Formalized methodologies don't blend well with highly nuanced heritage structures. On the other hand, the lack of procedural guidance, I'll say, has its downsides in that it leaves some folks in the profession very unmoored and unsure of what to do, and sometimes reaching for the wrong procedures that are incompatible with heritage structures. In general, the principles are obviously very conservation minded, and with respect to seismic aspects, they're unlike any document in the United States, perhaps with the closest being Preservation Brief 41. For those folks who practice in the US who are interested, Preservation Brief 41, while perhaps not perfect, is a really good start to bringing conservation mindedness into the seismic world. My view is that the principles ought to be self-evident to the segment of the engineering community that practices in the conservation seismic field, but it's clear that they're not, and you only have to look at the widespread use of ASCE 41 in the US, which really has not one whit of conservation mindedness in it, but it is regularly applied to heritage projects. Finally, on this note, in the US, there's no clear legal pathway to incorporate the principles into projects, which is somewhat problematic, and I think that that's the case largely around the world. Nonetheless, as people in charge of these projects, we can steer them in the general direction of the principles, if not incorporating them explicitly. So the first project I'm going to talk about was really initiated by the mineral earthquake in 2011, which some of you at least know caused damage to a number of monumental structures in Washington, D.C. The day after the earthquake, we were brought in to perform a damage assessment on what we believe to be the tallest unreinforced masonry structure in the world, otherwise known as the Washington Monument, which it turns out was damaged enough that it had to be closed for assessment and repair for 2.5 years following that earthquake. So while there wasn't a lot of damage to kind of more normal community-wide buildings, there was substantial damage to monumental type structures. That work ultimately led to us being asked to perform a seismic vulnerability assessment of the structure, and that's really what I'm going to be highlighting here, what I'm going to be talking about. A few of the principles that are highlighted by this are: do your research, respect heritage value, and credit inherent strengths. Don't be reflexive, think through the problem, because heritage structures are nuanced. And finally, respect the project criteria. I think that's a particularly key one here that I want to expand on. Essentially, we were asked, and this is important to understand what I'm going to be telling you, we were asked to determine if this historic, tallest unreinforced masonry building in the world really provided a level of seismic safety that was roughly equivalent to that of a new structure. Okay, so keep your eye on that ball, because that was the project goal, or that was our charge, and we didn't expand that charge. We kept to that charge, and keeping to one's charge on these projects is super important. Just so you can see a little bit about the research that we've done, I'm going to show you some of it, partly because it's pretty neat stuff, and partly because you can see how doing research informed this particular project. First of all, construction of the monument began around, I think, 1848 or so, and it was with private funding at the time, and it was in what has been called a swampy cattle pasture. They ran out of money after a few years, and construction ceased for about 25 years. But by the time it ceased, it was about 150 feet tall already, so pretty tall, and it was measurably out of plumb. Just so you know, the walls were about 15 feet thick at the base. The project, the construction of the monument, recommenced in around 1878, more than a decade after the Civil War had ended, And it was when the project was, at which time the project was taken over by the U.S. Army Corps of Engineers, and a very brilliant engineer with the name, who went by Lieutenant Colonel William Casey. The first thing Lieutenant Colonel William Casey did was to recognize that the foundation was very, very inadequate for a structure that was ultimately to rise to 555 feet tall. So he redesigned the structure and he redesigned the foundation. These are some pretty cool photographs from the era of the foundation strengthening. This is from when the foundation strengthening was complete. The monument was completed, its construction was completed in 1884, and by that time it had settled another 4 inches, but Colonel Casey had managed to return it to plumb, which I'll tell you was some trick, given that this stuff was all built by hand at the time, and it was a very heavy structure, 150 feet tall, and he managed to plumb it. We know an awful lot about the monument's construction, which I'm not going to take a lot of time to describe, other than to say that here you can read for yourselves, but understand that the top of the monument, the pyramidion, its structure is very, very different from the construction of the balance of the monument of the shaft. It's all unreinforced masonry, but the top is a very oddball structure. Most of the structurally significant damage from the mineral earthquake was concentrated in the pyramidion up at the top. So keep your eye on that ball as well. I found the coursing diagrams for the monument we found them in the HSR for the monument to be fascinating and very informative about how the monument was constructed, how the materials laid out within the monument. Very, very informative. Anyway, on the basis of everything we knew, we prepared some very, very detailed models in SketchUp, so we really could understand the geometry of the system, identify the various parts. I'm really just showing you the pyramidion portions of the SketchUp model. We also use the SketchUp model to provide a visual catalog of the damage that was caused by the mineral event, which included spalling and cracking of a lot of the stone in the top. On the basis of all of that as well, we developed nonlinear analysis models in SAP 2000, which I don't need to go into detail about to give you the crux of really what this project was about. Simultaneous with all that work, we were working closely with our partners in the geotechnical realm to study the seismological aspects of the earthquake and of the site. And not to jump to the punchline, don't take your eye off that ball, the seismological aspects. Essentially, in the top row here, and I don't expect you to get a lot of the detail, we looked at the attenuation relationships and concluded that an instrument in Reston, Virginia was at a similar epicentral distance as was the monument, and that instrument contained a significant amount of relevant data for understanding what the motion was at the site of the monument. We performed a probabilistic seismic hazard analysis and examined the seismology as well from a deterministic perspective. Like I said, I don't expect you to get everything on the slide, but I want to point out 2 things. If you look in the lower right-hand corner, maybe you can see down here that in the short period range, the green lines are substantially have a higher ordinate or much higher up, so higher spectral accelerations than the purple lines. The green lines represent the response spectrum deterministically determined from the mineral event at the site. The purple lines represent what's believed to have been an equivalent response spectrum from an event in 1886 as far away as Charleston, South Carolina. If you look in the long period part of the spectrum, you'll see that the purple lines from Charleston substantially exceed the ordinates of the green lines from mineral. So hold that thought once again, because this is a key aspect of our work and our findings. This response spectrum is a primary product of the seismological study. I'll show you the legend. There's a lot of curves on this slide. Bear with me. I'll show you the legend for what those curves mean in one moment. But first, I want to point out that superimposed on this response spectrum is the data, is some of the data that was output by the structural modal analysis. And essentially, you can see that the period of the first mode of the monument, which essentially is the swaying of the shaft, the long period response, is out at about 3 seconds. You can also see that the modes for the pyramidion, which frankly has a very complex response and involves a whole lot of modes, is centered at around 0.3 seconds. So keep that in mind. Hold that thought. If you look at the legend for a second, and there's still more things on this slide than you need to focus on, first thing I want to point out is the dashed black line, which is the maximum considered, the risk-adjusted maximum considered earthquake for the USGS. This is the 2475-year return period earthquake. So that's really the basic earthquake that we designed based on, and in the US, we designed based on 2/3 of that number. So that's the MCE, the risk-adjusted MCE. The next thing you should look at, if you look at either the dashed blue line or the dashed purple line, these are representations of the site response of the Washington Monument, which sits on the National Mall. And those two lines were calculated in different ways. But the key point to see here is that those lines substantially exceeded the MCE in the short period range and were substantially less than the MCE in the first mode. Make sense? Of note here, the reason the MCE is so much larger than the other lines in the first mode, that's really a consequence of what's believed to be the motions at the site from that 1886 Charleston earthquake. Here's the last slide I'm going to give you before the conclusions, really. We are that close. I just haven't told you the punchline yet. This is another representation of the motions in ADRS format, in which the thick turquoise-like color line is the best estimate of the site response spectrum from the 2011 mineral earthquake, and the thick dark blue line is the best estimate of the response spectrum for the MCE motions, which include the 1886 Charleston earthquake. I think this slide tells the story most clearly. During mineral, the pyramidion modes were excited to a greater extent than they would have been even by the MCE. But the shaft was barely excited at all relative to the MCE. However, the shaft mode is right there at the peak of the Charleston response spectrum. So the conclusions are these. The seismic vulnerability criteria for the monument were really satisfied. This structure can be argued to be as safe as a new structure. Why? Because the pyramidion experienced its MCE in 2011, and the shaft experienced its MCE in 1886. Done, right? You can kind of wash your hands of it. I will tell you in closing on this particular aspect that we did recommend that certain additions be made to the pyramidion just solely to account for potential for directionality differences between some future MCE and the MCE we just experienced. So that's it for that subject. I don't know how much more time I have. Looks like I got about 15 minutes, I think. So let's hit the next one. This is the ordinance required strengthening of Shereth Israel, which is a synagogue in San Francisco. The highlighted principles for this particular project are respect heritage value, minimize disruption is a design priority, and consider bespoke systems and innovative materials to achieve your goals. Okay, this is one of my favorite photos ever of this particular project, and really of almost any project I've ever worked on. I like to note when I talk about this image that this was taken after the project was completed. But frankly, it could have been taken before we started the project, and you'd never know. Because nothing you see, despite the fact that we did a ton of things, we did a ton of interventions to this building to make it more seismically adequate than it was when we started, nothing you see in this photograph was demolished, rebuilt, replaced, or damaged. Nothing. Other than there was some paint that was improved because there were some old water stains from roof leaks, but nothing was changed. Now that might not sound particularly special to any of you, but it will, I think, once you see the next slide, because that sanctuary space that I was telling you actually occupies about 85% of the plan area of the structure, which didn't leave us a whole lot of places to actually do our seismic interventions. In addition to the very significant areas highlighted here in blue, which was the sanctuary, other areas, for example, the one at the top of the screen, which is the organ room for a very historically significant Murray Harris organ, was completely off limits. So in total, the off limits areas, I would say, exceeded about 90% of the plan area of the building, which made it a pretty tough place to do a lot of interventions, which is one of the things that's special about this project. But I'm only going to describe to you one of the interventions during this talk. But first, I want to give you a little bit of context about the structure so you understand kind of how we got to where we are. First of all, this is a roughly 1904 unreinforced brick masonry building, bearing wall building with some steel framing. As you can see, some very light, flimsy steel framing in the interior space with a Calusa sandstone facade. The engineer and the architect was the very brilliant Albert Peisis, who actually designed a number of major buildings in San Francisco that survived the great earthquake in 1906. The guy just had a kind of proven trial by fire record. Unbelievable. And all without a computer. So you understand a little bit more about the structure. I want you to see this. This is a diagram that really shows the upper level steel framing at the balcony plan and the drum above. You can see the highly articulated roof. This is not a trivial structure size-wise. It's not as large as the monument, but it's still 120 feet tall at the top of the dome. It's 100 feet above the top of the dome is 100 feet above the sanctuary floor, and the main masonry bearing walls are 65 to 75 feet tall. So fairly large. Notably, it also has very flexible wood diaphragms, and they're flexible not just because they're wood, but because of the sanctuary space at the balcony level and through the dome, there are these very large openings in the diaphragm. So we have very flexible floor systems supporting the walls out of plane, which drives a fair amount of the response. When the building went through the 1906 earthquake, it did pretty well, but it was damaged for sure. And a lot of the scars of that damage are still in the building today. I love this particular photo that shows that a lot of the cornice was thrown from the building. There's really a lot more damage than you can see in this photograph. These walls functionally, with flexible diaphragms to support them out of plane, they bow outward. During seismic events, they bow significantly, and because they are articulated and planned, they try and unfold, right? They try and catenary to a degree. We demonstrated that is actually true, that the damage we see in the attic space today from the unfolding of this wall and the outer plane of all four walls really in the outer plane bowing behavior is real. It's predictable analytically. And we think a lot of this behavior is also driven, interestingly, by the excitation of the drum and dome. And when it tries to sway back and forth, it pounds on the gable roof sections, and those kind of pound against the gable end walls and help to push those things out of plane, which is not a great behavior mode. Lots of other behavior modes in this thing that I could talk about, but because I'm only talking about one intervention, I'm only talking about that behavior mode. Now, we knew it's pretty intuitively obvious that one way to help control that behavior mode is to put in tension ties. But we took one look at the thing and said, well, that would be pretty ugly, pretty disruptive. So we tried to really improve on this traditional system, the way it's been used around the world. We wanted to avoid disruption to the sanctuary, and we wanted to neutralize some of the disadvantages of using steel or iron, because those things undergo plastic. You have a choice, right? You can either make them very strong and stiff, in which case the odds are they're going to pull out of the walls at where they're connected. Those connections will fail. Or you can make them less stiff and less strong and let them yield. But then after a single cycle of response, your walls are now, they're out of plane, and there's no ability to bring them back into their original position. So we got creative, and we put in a tension tie system that was above the ceiling of the sanctuary and circumvented that open area, the interior drum. That system consisted of an octagonal tension ring, essentially with some outriggers that were composed of steel and nitinol harps, which I'll describe in one moment, but 4 nitinol harps, one in each quadrant, essentially, of the structure, one to support each of the exterior masonry walls. And note that by statics, when you look at this, if one wall tries to move outward and fall out of plane into the street, the nitinol actually gets engaged. These harps get engaged, on all 4 of them get engaged with the movement of only one wall. So structurally, it's really very efficient. Nitinol, for those of you who don't know, is a super elastic material. It's magic metal. I mean, this stuff is the coolest stuff you could ever work with. You can stretch this. If you stretch steel out to 6%, you have mostly non-recoverable residual deformation. But if you stretch nitinol out to 6% and let go, it'll bounce right back to the way it started. So this stuff as a material relative to the masonry has tremendous capability to, and relative to this building has wonderful capability to do a lot of things, which I'll describe in one second. But we went through a whole, while the properties of nitinol are fairly well established, we went through a fairly elaborate testing program in-house to validate that this would work for us. And these are the load displacement curves really for the nitinol in our lab. And you can see we're stretching it out to 6%. And when we let it go, it goes back to 0. I mean, it's magical stuff. This is an image of kind of where it was placed, of one of these harps above the ceiling, so completely invisible to occupants. None of this crosses the sanctuary space. And at the end of the day, this is kind of a poorly conceived graphic of mine, but whatever, my PowerPoint skills are somewhat limited. What this ultimately does, it not only resists the out-of-phase outward behavior of opposing walls, but it promotes recentering, right? Which is kind of like this is a goal of seismic response that we'd like to install in many structures to get them to recenter. But it improves the global wall stability, and essentially it helps to cinch up the whole roof diaphragm, where we have all these this giant opening in the middle, all while avoiding disruption to the sanctuary. Now, I've got 5 minutes left, right, guys? So maybe I'll hit this for a couple of minutes.
Yeah, you got time, Terry.
All right. So I exceeded my own best expectations. So the post-earthquake repair project is of the Washington National Cathedral. This too was damaged by the same event that the Washington Monument was damaged by. It's worth noting that you look at this, that this building has an extraordinary number of pinnacles on it. This is all unreinforced masonry as well. Extraordinary number of pinnacles everywhere you look, which I'll talk about in a few seconds. The highlighted principles for this, again, are respect heritage value. Again, respect the project criteria, which here were, we don't want to do a seismic upgrade of the building. We want you to fix the damage and not do much more than that, and also minimize interventions. So I mentioned before, this building has a lot of pinnacles. It has a lot of turrets and other features. In some cases, it has so many pinnacles, the pinnacles even have pinnacles. They're all over the place. Many of them were damaged. And I'm not going to show you a broad swath of that, but they were some of them, the upper courses fell to the street or fell and hit the roof. Some were just dislodged. Some just rocked back and forth, but all over this structure, pinnacles and towers and turrets were damaged. And some very significantly, you can see here, this thing was really kind of teetering, this very bad shape. And this is a huge, weighs many metric tons, a massive item. At the very top of the Washington National Cathedral, about 300 feet in the air. Again, very significant damage with very heavy masonry elements, just ready to fall 300 feet down. So this was, I mean, to me, just mind-blowing stuff. Luckily, the earthquake stopped before it actually fell. So let me just tell you our approach, which I think I can tell fairly briefly. If you think about this as a problem, you have to recognize, or you ought to recognize, that when material was shed from the tops of some of these pinnacles, that acted as a fuse that actually relieved the vulnerability of the joints below. Where the material fell, it was a significant hazard, but it actually relieved some of the problem. The problem for us from a repair perspective was that reestablishment of the joint as it was before would leave the pinnacle with the same vulnerability and hazard, which really was right on the edge of being disastrous in many cases. But strengthening the joint could also increase the vulnerability by causing yet more material to dislodge during the next earthquake. So the solution here was to assess the transfer function for the pinnacles, which was actually fairly simple, which I'll explain to you why it was so simple. We did this all without developing a fancy structural model, and reinforce these pinnacles and towers and turrets down to where the MCE would not cause material to fall. Essentially, when you think about these pinnacles, there's a bunch of, coursing here, and each course has a certain weight, right? So we can easily calculate by hand the weight of the system, if you will, at each bed joint. We can also calculate the resisting moment to overturning from the dead weight, from the dead load of the masonry. So we both know, we know the weight, we know the resisting moment. We now know for any joint in these structures, for any bed joint that was damaged by the earthquake, we now know the transfer function, right? We know because we know what the site motion was. We just didn't know what it was up at the tops of these pinnacles. But knowing where the damage was and what the resisting moment was, we now have a pretty good estimate of the transfer function for that level. So essentially, all we did was develop Excel spreadsheets, try and understand what the tipping acceleration would be at any bed joint elevation, and develop strengthening techniques which consisted largely of center cores, and install them down to the level where we believe we would not be increasing the hazard, but just to that level, right? So that we kept the hazard where it was, we could resist the MCE motions, and the pinnacle below that we believed was stable by virtue of its own dead weight. Hopefully that makes sense. I think that's the end of my presentation.
Thank you so much, Terry, and right on time. And you got all your 3 projects in. That's very impressive. And the projects were probably even more. Arun and Casey, please also join the panel. We will have a series of questions from the audience and a couple of comments. And at first, I'd like to see that say that I really loved some of the true lines in all of these presentations. And that is that, both of you started with a thorough analysis, right? That full understanding of structural and material characteristics of the structures you worked on. And that is really the first thing that these Iscarsah principles demand. And then the detailed analysis before going into an intervention, trying to find the minimal intervention in your projects and balancing these old and new materials. And those tenets are, I believe, Terry, you said it well, that a lot of what we do, we don't explicitly use these Iscarsah principles, but we have them in the back of our minds and we use them whenever we can use our engineering judgment. So I don't know if you want to make any other comments on that or if we should go into the questions of the audience.
I have a quick question that's associated with that, just with this idea of using engineering principles and the Iscarsah principles and judgment. Do you feel like it's getting harder to do that with some of the more stringent code requirements, or has it always been the case? Are we more limited in terms of our ability to use engineering judgment on these types of projects? I guess that's for any or all 3 of you.
Arun, you want to take the first shot?
Yeah, I would say that's a question that really nails it, because I think with the seismic standards becoming more and more restrictive in terms of what can be done, not only in new designs but also in existing buildings, I think there's a demand on studying historical constructions, existing constructions in a more in a deeper sense in trying to understand better these traditional construction systems, to be able to preserve them without completely transforming them into monsters, if you want, through engineering interventions. So I think it's an interesting space that we are in.
Yeah, and Rachel, if I can add to that, I mean, I have a couple thoughts in mind that I think are important to get out. One of which I kind of I mentioned during my presentation. I mean, standardized procedures can definitely get in the way, right? When we're working on heritage structures, because the heritage structures are so nuanced, you can't write procedures that are applicable to all of them. It just don't make sense. On the other hand, we have left the profession hanging in many respects without adequate guidance. And as a result, engineers often reach for incorrect standards and incorrect procedures, inappropriate ones, when they're charged with working on heritage structures. So that's a problem. We need something. I think we need something to help, maybe not formalized procedures, but something that provides some structure for thinking about these projects and how to address them. I forget what the other thing I was going to say, so I'll just shut up.
Thank you. Arun, there was a very specific, Arun and Casey, there was a very specific question for you from Rob Bellardi, and that was if epoxy was used to anchor the rods to the joists in the brick. And I would like to add to that, right? And this comes also back to Terry's presentation, that in your case, Arun, Arun and Casey, you used rods and maybe epoxy or not. Terry, you used this nidinol new materials. The principles talk about finding this balance between using traditional techniques and new materials. Could you comment on that and how you decided to use these new materials?
I don't know, Casey, would you like to go?
Yeah, I mean, say, for example, it completely depends on what the system is demanding. So in the earlier days when I started my career, it was something like questioning the existing load path. But over a time, it's understanding the load path, accepting the load path. I mean, accepting the structure as it is, and what is required to help that structure, or what is required to improve that structure. So in this regard, at sometimes the interventions required will be very much minimal, since we will be looking at only helping or enhancing the capacity of the structure. So with respect to that aspect, when we are looking at the existing solutions available, what is the best for the system? That's all. That's how I see that aspect.
And did you use epoxy
Yeah.
with the balls? Or?
So to specifically answer that, I think there was no epoxy. It was just dry installation, because it would just go through the timber and then into the brickwork. So it was just friction that was really working there. Yeah.
Tim, can I go back to something you said just a few moments ago?
Absolutely.
I don't want to hijack this, but so you highlighted the analytical aspects of things. I do want to point out that, you know, we can sometimes as engineers get very lost in analysis, and just to kind of make sure everybody understands, when you look at the Washington Monument Project, yeah, we did analysis, but you know what? The answer was really in the seismological side of the question, right? All the analysis really informed us was about the modes of vibration of the structure. The stress predictions, the displacement predictions, I mean, none of that really mattered. You know, the hardcore aspects of the analysis were not that relevant. This was a seismological conclusion. We compared the MCE to the 2011 earthquake and to the 1886 earthquake. The problem solved, you're done. Almost similarly, in a similar vein with the Washington National Cathedral, we used Excel. It was just an Excel spreadsheet, and we calculated gravity loads and moments. It was that simple. This was not reliant on high level analysis. And so, you know, high level analysis can be informative, but it may not be necessary on all your projects.
I think that's a great point, and I think we need to focus on that holistic analysis and understanding of the building, right? And not get too lost in extremely complicated models, but keep the broader view.
I think that's, oh, sorry, Tim. I was going to say, I think that's really important, especially since we, to Arun and KC, are David Pichetti Award winners, right? That was his whole approach to preservation engineering, is really a practicality and sort of asking the structure. So I think that it's a through line through all of these, and I'm excited to hear that's how most folks are approaching these buildings.
One other question from Mustafa Humo for Arun and KC, and was whether there were examples of earthquake damages to these slabs of the Madras system.
In the southern peninsular India, it's rare to find large earthquakes, and you don't see this sort of, at least in the recent years, this sort of a damage. But then there are similar systems that you can see in more earthquake-prone zones, and in the Nepal earthquake, there were some examples that were comparable.
Thank you.
Thanks.
Terry, we also had a question about the nitinol harps and whether they're original to the structure. I believe you explained they were additions, right? But could you comment a bit more on that and maybe explain like how you came to that material? And do you know something about the long-term performance of that material or checks you need to do on that? Or could you explain a bit more?
Yeah, sure. So that whole tension tie system was a remediation effort. There were no tension ties in the original structure of any sort. And, you know, as I said, utilizing kind of traditional technology, tension ties would have crossed that lovely sanctuary space and maybe not look so great. So the system was developed to kind of provide tension tie capability without disrupting the look of the place, the look and feel. The nitinol was selected because we recognized from the outset. See, I've always had, I'll just tell you, and this may be a digression, but may be important for everybody to hear. My belief is you really can't, you shouldn't be trying to change these heritage structures into something they are not. They come into being basically with a certain mass and with a certain stiffness, and that's what they are. You're never gonna, unless you fill them with shear walls, they're gonna have that mass and that stiffness, and you're stuck with it. So you can't change that, right? So you have to work with that rather than try and change it. This building, Sherith Israel, one of the things we were stuck with is walls that want to bow out of plane. That's what they do. We recognize that to try and stop them from doing that would potentially vastly change how the structure has always worked. And we know it worked pretty well in 1906. I mean, it's not like it's a bad building. So we wanted, I thought of this, the tension tie system almost like a shoulder harness in your car, right? When you're sitting in your front seat, it's the thing that stops you from hitting the steering wheel. The tension tie system is the thing that stops the walls from falling into the street. It restrains them, but it still lets them move because what they want to do is move. You can't stop them you're never going to stop them from moving without doing damage. So anyway, that was the overall philosophy. And the nitinol helped us achieve that because it has this amazing flexibility to it, number one, if you will. But it also, the stretchability, but it also has, see, the problem with steel is once it stretches, it doesn't unstretch. So every cycle of the earthquake, the walls will move progressively farther and farther out of plane toward instability. Our goal was to try and make them not move progressively toward the point of instability, but rather to pull them back in every cycle of the earthquake. And okay, now I'll shut up because other people want to talk.
I had a quick question for Terry, if I may.
Of course.
Yeah. So, I took Professor Collins' course when I was in Pavia, and one of the three principles he started his classes with is that you cannot push on a rope. So, when you're looking at the nitinol elements, you're expecting only tension in that configuration, or can there be compression in some cases? And if so, where is the stiffness and compression coming from?
We don't believe we need stiffness and compression, and that's really, I think, one practical way to explain it is to say, how many times after earthquakes have we seen masonry walls fall into buildings? They don't. They fall outward. They fall outward. So that's what we're trying to address. We believe the risk of falling inward is negligible by comparison.
Thanks.
I would like to encourage participants to post additional questions in the chat. Rachel, did you have anything you wanted to bring up? Should I go?
Well, I guess I've seen this in the chat, but and it's not necessarily a technical question, but asking this group, will anybody be submitting for the Pachetti Award again? Hopefully. When did you learn anything from each of these three projects, Terry, that was incorporated into the next one? These were not presented in the order, right? That you've like done them. is there anything that you learned from the Washington or Sheriff Israel that got incorporated into the Washington Monument, or any sort of lessons learned?
Not that I can fairly transmit. I mean, look,
Okay.
The lesson I learned is that my instincts are pretty good, and on every project, you know, the outcome seems to be successful, and they all involve kind of putting down the books, putting down the methodologies, putting down the procedures, and looking at every project afresh. What are the project criteria? What do we need to do to satisfy the project criteria? And this requires an open mind, a complete, almost a blank mind, right? You have to be open to different approaches on the analysis side, on the intervention side, as I said, bespoke systems, right? Be open to customizing a brand new solution when that's the best thing to avoid disruption to the heritage value. You have to be open to shopping around for materials that help you minimize disruption to heritage value. And just so on all these projects, just try and keep an open mind and not be bound by what's been done before.
I do have another question for Arun and KC. What was probably the most surprising thing that you found in your analysis and implementation of the repairs on that project? I'm going to ask the tough ones, I guess.
No. So I'll let Casey also come in here. But the amazing thing was with a very minimalistic type of intervention, you could dramatically change the behavior of this sort of a system, and it's such a well thought out composition that. It's so easy to dismantle the whole thing and sort of put it back. I mean, conceive the way it works, conceive different parts work. So that was the most surprising thing, that something as small as a pin could actually totally change the way the system was working. And that sort of reinforced this concept of minimalistic interventions. That for me was probably the most important takeaway from the study. Yeah, Casey, if you have.
And for me, it was something like there is for practicing engineers, there is this tendency of replacing the system when they find that something is not working good with respect to the system. So that tendency is there. So when we were able to prove that, yeah, with respect to this much cost and with this much minimal interventions, we are able to upgrade this traditional structural system. It was something kind of very much satisfying for me.
I have my hand up if there's no other question I'd love to ask. For Arun, actually, NKC. So if I understood your work correctly, you had essentially a slip plane between call it the masonry system and the timber originally when you started. I don't know the extent to which that slip plane is important for allowing the masonry to change dimensionally, change size dimensionally, shrink, breathe under thermal, whatever. But it seems to me that when you put your shear connectors in there, that there is a change in the system that occurs relative to its breathability. Have you considered that? And what are your thoughts on that subject, as whether this may introduce some potential for cracking long term, et cetera?
I was expecting that googly from Terry, and we sort of thought about this quite a bit. The anchors were dry installations, but still they had a plastic sleeve, and so hard contact was avoided. Having said that, the other aspect in terms of thermal movements, shrinkage and expansion, these constructions, and that probably answers one of the other questions that was there in the chat, in terms of what is the dimension of these, what governs the dimensions of these slabs. That the largest of these would be about 10 feet, 3 meters plus. And that's because of the size in which you would get these rafters, the length in which you would get these rafters. So for over about 10 meters, when you're looking at an interior slab system, the shrinkage is really expansion and contraction is really small. If you consider this on the terrace, yes, it's going to be exposed to a thermal gradient that's much more, but then you have a large cross section of lime concrete that's sitting there, and so that's again a good amount of insulation. So with the soft interface that the plastic can bring in, and the limited sizes of these spans, we'll have to run some numbers there, but I don't think it can completely restrain the minimal movement that's expected due to thermal variation. Yeah.
Thanks, Arun. If I can follow up on that with a question that Amy Woods posted, whether you could comment on the material properties of the mortars, the lime mortar, clay mortar in the slab. What type of mortar was used here and how does it affect properties?
Yes, you want to take that?
So the question is about the material properties, how this is playing into the analysis, right? So we basically, when we are doing the numerical analysis, we are going for a smeared model where the properties of the lime mortar, the brick masonry overlay, everything will be smeared over in the thickness of all these overlays. So it won't be something like a detailed modeling approach where we are considering all these explicitly, the joints explicitly, everything like that. But we were going for a smeared macro modeling where the specific properties of lime mortar, brick masonry overlay, as well as the timber joists were taken into consideration.
And to just add to that, as long as we were getting the geometry right and possibly the elastic modulus of the composite, I think we were there. We really didn't have to worry too much about the material properties beyond that.
Thank you. And Terry,
can I add one thing to that? Just not an answer to that question, but just as a plug for the next PETC webinar is about material research and how that plays into our analysis. So I know you've seen a lot of Tom Morrison in the chat here, but he's going to be one of the presenters in that presentation as well. So timely question.
I wanted to follow up with a question from Niki Miltiadou from Greece to Terry, saying that in Greece they have seen collapses inward of masonry, and she commented that why not combine your intervention with additional elements of resisting compression? In Greece, we combine steel with wooden systems of ties. So
I think the answer still is we're not, our interventions are not intended to prevent everything that's possible, right? Our primary job is to intervene in what's most likely. In this particular structure, there were lots of things we didn't do because the risks were judged to be relatively less. Sometimes we, when we're trying to balance interventions against loss of heritage value, we have to temper our desire to kind of do more Although I can envision, in response to the question, there probably were some ways we could have installed some compression capability, but I think it would have been complex here because the compression system would have butted up against the huge opening in the diaphragm, and not a really good way. So just to back up, one of the priorities for one of the criteria for installing this tension tie system was to keep that steel very light so that 2 guys could carry every piece. A maximum of 2 workmen could carry every piece, so that we didn't do any welding up there. We didn't use any torches. This was part of the criterion because it was a fire trap. So we wanted to keep everything really light. And that meant the members we were using were really good in tension, but not really good in compression. Not just the nitinol, but even the structural framing members. As soon as if the goal here was to also resist interior falling of the walls with structural members, I think we would have had to have added some pretty heavy stuff to make that happen and somehow transmit those forces around the big opening in the diaphragm, which right now, I don't know how we would have done without substantially more disruption to heritage value.
And I think that is a crucial point, right? And that is that as engineers working on these heritage sites, we always need to weigh the pros and cons of a minimal intervention, doing slightly more, the risks involved, the damage we do to the building, our responsibility towards life safety, right? That buildings cannot collapse and kill people. There's so many conflicting interests at times. We really need to balance those. And for every project, those outcomes will be different. And, I was very impressed, Terry, for example, with you deciding essentially not to do anything at the Washington Monument, right? That was the result of the study. And that is, I believe, that is brave. And I would like to give you another compliment for that. I also think we're very close to time. So I don't know, Rachel, if you want to make any closing comments, our final questions.
No, I mean, I think this is really great. I hope this is the first of many in terms of collaborations. I think we've seen with the questions and the conversations that have come out of this, there is so much overlap between these 2 organizations. And so really looking forward to having future conversations about many of these topics.
Great.
Thank you so much to our speakers. This is fantastic.
For those who don't know, it is getting very close to midnight in India. So again, Arun and Casey, we really appreciate you accommodating our schedule. Terry is on the west coast of the US, so getting this planned was challenging, and we appreciate the time and all the effort you spent. Thank you to all the participants for your active participation and all your insightful questions. This webinar will probably end up on our YouTube channel, where we have also recordings of past Iscarsah webinars. Thank you very much, everyone.
Thank you.
Thank you.
Thank you very much.
Thank you very much. Thank you. Bye-bye.